Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. So what we are working on today is inverse trigonometry, how we can find their derivatives. Specifically, we're working with inverse cosecant, inverse secant, and inverse cotangent. So let's go ahead and dive into it. We want to find the derivative of the inverse cosecant. So when we are doing this, it's going to be a very similar process as in the previous video. So first, what we're going to do is take cosecant of both sides in order to get rid of that inverse. So when I do that, I get cosecant of y is equal to x, because that cosecant and inverse cosecant, they like kind of cancel each other out. So what we're going to do here is implicit differentiation. So I'm going to go ahead and take the derivative of both sides in terms of x. So on this left-hand side, what I actually want to use is chain rule, right? Our inside is equal to y, and our outside, g of u, is equal to cosecant of u. So when I take the first derivative of y, remember we're taking the derivative of y in terms of x, which means we actually can't take the derivative. It's not going to equal 1. I'm just going to leave it as the first derivative of y prime. And then my derivative of cosecant is equal to negative cosecant of u times cotangent of u. So when I plug all of this in, I get y prime times, and then we got negative cosecant, but instead of u, I'm going to plug that back in. So I get y times cotangent of y. And now let's go ahead and take the derivative of the right-hand side. So we can take the derivative of x in terms of x, right? And we get a value of 1. So remember, what we're trying to solve for here is y prime. So what I'm going to do is I'm going to divide over that negative cosecant, yada, yada, yada. So here we can actually plug something else in, and that's what x is equal to. So x right here is equal to cosecant of y, and we can replace that in our derivative. So here we're almost done. We have cotangent of y in the derivative, and I don't want anything in terms of y. I want it all to be in terms of x. So actually what we're going to use is this trig identity right here, where sine squared y plus cosine squared y is equal to 1. And so I want to go ahead and find cotangent. I'm going to do that by dividing everything by sine squared. So when I do that, I get 1 plus cotangent squared of y is equal to cosecant squared of y. And remember, cosecant of y is equal to x. So if I replace that, I get 1 plus cotangent squared y is equal to x squared. And so here, what I want to do is solve for cotangent. So I'm going to go ahead and do that. So now I have what cotangent is equal to, and I have it in terms of x. So I can go ahead and replace that in my derivative. So I get y prime is equal to negative 1, and all of this is over x times the square root of x squared minus 1. So this actually gives us a constraint, because remember, we cannot take the square root of a negative value. So this constraint tells me that x squared minus 1 needs to be greater than or equal to 0. So let's go ahead and add 1 to both sides. I get x squared has to be greater than or equal to 1, and that results in 2 conditions. So our 2 conditions here is that x is less than or equal to negative 1, so negative 2, negative 3, negative 4. And I also have that x has to be greater than or equal to 1, 1, 2, 3, 4. So here I have the graph of inverse cosecant. Let me write that out. And I want to think about the derivatives, okay? So when I think about the derivatives, I have to think about the slope of the tangent lines. So let's go ahead and take the slope right here. If I were to draw on that tangent line, right, it would look something like this. And if I look at the slope, that's going to have a negative slope, which this implies that we need to have a negative derivative. So let's look similarly on this side, right? If I were to find the tangent line right here, it would look something like this, which again, this has a negative slope, which means the same thing, that we need to have a negative derivative. Alrighty, so let's go ahead and think about this in terms of our derivative y prime. If I were to plug in a positive number, so right here and right here, I would end up with a negative value because we have this negative 1 right here. So I already know when I plug in a positive value, I'll get a negative output. But what happens when I plug in a negative value? So right here we have plug in x equals -2 into y prime. And remember, we want that derivative to be negative. So when I do that, I get y prime is equal to -1. And then we have x, which is -2, times the square root of -2 squared, which that is 4 minus 1. So here we have two negatives which end up canceling out. So we get 1 over 2 times the square root of 3. I don't really care what this necessarily equals. All I care about is that this is positive. But like we talked about earlier, we wanted we wanted y prime to be less than 0. We wanted a negative derivative. So how do we keep this negative? We keep it negative by adding absolute values to the x, because now that becomes +2 in the denominator, which keeps the numerator negative. And so this ends up being negative. So this is the rule that we're going to use. So the derivative of inverse cosecant is -1 over the absolute value of x times the square root of x squared minus 1. So that is a little tricky constraint that we have to have on our derivative in order to keep all of the slopes negative. So that -1 in the numerator always dominates. Okay, so here we have an example so we can kind of put this into action. So here we want to find y prime of inverse cosecant of the natural log of x. So let's go ahead and set up chain rule. We have our inside is going to be equal to the natural log of x. The outside g of u is going to be cosecant inverse of u. So let's go ahead and find these derivatives. U prime is going to be 1 over x because that's the derivative of natural log of x. And g prime of u is going to be using our new rule. Let's go ahead and plug all of these in. So y prime is equal to u prime, which is 1 over x. And we're going to multiply that by g prime. So here I get -1. And all of this is going to be over the absolute value of the natural log of x. Remember, we're plugging u back in. And then all of this times the square root of the natural log of x squared minus 1. And that is our solution. So secondly now, what we're going to do is find y prime of inverse secant. And we're going to use a similar process. So I'm going to take secant of both sides, and I get secant of y is equal to x. And now we're going to go ahead and use implicit differentiation. So I'm not going to set up chain rule explicitly this time. I know this is going to turn into y prime times, and now let's take the derivative of secant. That is equal to secant of the inside times tangent of the inside. And now when I take the derivative of x, I get a value of 1. So remember, we're trying to solve for y prime, and I'm going to do that by dividing over that secant tangent. So I get 1 over, and now I have secant of y times tangent of y. Now we can go ahead and plug back in what we know. I know secant of y is equal to x, and I can replace that in my equation right here. So I get y prime is equal to 1 over, and that becomes x times tangent of y. So again, we're going to use this identity, and we're going to try to solve for tangent of y, because I don't want any y's to be in my equation. So in order to get tangent, I need to divide this one by cosine squared. But I need to divide everything by cosine squared because I can't just divide one thing. Alrighty, so let's plug in what we know. I know secant of y is equal to x squared, so this becomes x squared. And then tangent squared of y plus 1 remains the same. So I'm going to go ahead and solve for tangent. So now I can plug this back into the equation. So I get y prime is equal to 1 over. And now we have the exact same constraint as we had last time. So here what we need is that x squared minus 1 needs to be greater than or equal to 0, because again, we can't take the square root of a negative value. So this again has two results, right? X has to be less than or equal to -1, and x also has to be greater than or equal to +1. So here I have the beautiful graph of inverse secant of x, and we are going to again talk about its tangent lines, because we want to know if the derivative needs to be positive or if it needs to be negative. So let's look right here on this value. If I apply the tangent line right here, let's think about the slope. This has a positive slope, right? And a positive slope tells us that we have to have a positive derivative. If I look on our other side right here, if we find the tangent line, we're going to have the exact same case, right? I can see I have a positive slope, which means I need a positive derivative. So if I look at our actual derivative we have right here, let's think about when we plug in a positive x value. This will be positive, this will be positive, 1 is already positive. I'm going to result in a positive derivative. But what happens when we plug in a negative value? Let's go ahead and try it out. We're going to try plugging in x equals -2 into the derivative. And remember, we want y prime to be greater than 0. So when I do that, I get y prime is equal to 1 over -2 times -2 squared, which becomes 4 minus 1. This is equal to -1 over 2 root 3, which this is indeed negative. So the question is, how can we keep this positive? And it's going to be the exact same thing. We're going to put this in absolute values so that this becomes positive. And that fixes what we're looking at here. So this gives us our rule. We have that the derivative of inverse secant is equal to +1, and then over the absolute value of x times the square root of x squared minus 1. So let's see this in action. Here we want to find y prime of inverse secant of e to the 4x. So let's go ahead and apply chain rule. We have our inside u is going to be e to the 4x. And then our outside g of u is going to be inverse secant of u. So let's go ahead and find these derivatives. Here we get u prime is equal to 4 times e to the 4x. I just multiply it by the derivative of the exponent. So the derivative of 4x is just 4. G prime of u is going to be our rule. So here we get 1 over. So let's go ahead and fill this in. I get y prime is equal to u prime, so 4e to the 4x. And we're going to multiply this by g prime of u. But remember, we're going to plug u back in. So I get the absolute value of e to the 4x times the square root of e to the 4x quantity squared minus 1. If you wanted to clean this up a little bit, you could. You could put that 4e to the 4x in the numerator, and all of this is divided by that same denominator. Voila, beautiful. Alrighty, everyone, we have one more. We want to find the derivative, or y prime, of inverse cotangent. And again, we're going to follow the same process. So here, when we do that, I get cotangent of y is equal to x. We're going to take the derivative of both sides in terms of x. Okay, so again, I'm not going to use chain rule explicitly. So I get y prime times, and we get the derivative of cotangent is negative cosecant squared at the inside. So I want to get y prime all by itself. I'm just going to go ahead and divide that whole term over. So I get y prime equals, I'll bring that negative to the numerator, and then we get cosecant squared y in the denominator. So this is what we want to solve for. I want to get that cosecant squared y out of there. So let's go ahead and try to get cotangent. So I know to get cotangent, I want to divide that by sine squared, which means I need to divide everything by sine squared. So here I get 1 plus cotangent squared y is equal to cosecant squared of y. Let's go ahead and plug in what we know. I know cotangent is equal to x. And so this cotangent squared is going to become x squared. And then I get 1 plus x squared equals cosecant squared y. And that's exactly what we wanted to find, right? That's what I want to plug in. So when I do that, I get y prime is equal to, we have that -1 still in the numerator, but now the denominator becomes 1 plus x squared. So there's nothing fishy we have to do with this one. That's just going to be our rule. We get -1 over 1 plus x squared, and that is our solution. So we have one more example so we can see this in action, and again, it's going to be chain rule. So I'm going to set my inside u equal to 6x squared minus x, and then my inside g of u, my outside, is going to be inverse cotangent. Let's go ahead and solve for these derivatives. So I get u prime is equal to 12x minus 1, and then g prime of u is going to be our rule. Let's go ahead and use these to find the derivative. So we get y prime is equal to, and now I multiply 12x minus 1 times -1, and all of this is going to be over 1 plus, and I have to plug u back in. So I get 6x squared minus x quantity squared. If you wanted to rewrite that, we could. We have -1 times 12x minus 1 in the numerator, and then all of this is divided by 1 plus 6x squared minus x quantity squared. How far you need to go depends on your teacher. I'm just going to go ahead and stop right there. But that is all I had for you today. If you enjoyed this video, please leave a thumbs up, and I have many more videos like it, so check it out. The playlists are linked below. Otherwise, thanks for watching.